Hi, welcome to the Euclidean Geometry 101 course. A completely new chapter awaits us, and yes, it is so new that we need an additional Euclidean postulate to introduce it. We will talk now about parallel lines. The postulate we are going to elaborate on is the fifth postulate in this course and also the fifth postulate in Euclid's Elements. It is arguably the postulate that has been debated the most in the mathematical community, and we call it the parallel postulate. Actually, though we call it that, Euclid doesn't mention the word parallel at all in it. Euclid formulated this postulate in the following manner. If two straight lines intersect a third line, and the sum of the two interior angles on the same side is less than two right angles, then the two straight lines will meet each other at a finite distance, if extended. As you can see, no mention of parallel lines anywhere. We can define parallel lines as lines that do not comply with the parallel postulate as formulated by Euclid. Indeed, parallel lines are straight lines in the same plane that do not intersect. There is a well-known mathematical symbol for parallelism, by the way. In the following millennia, this postulate has been reformulated in many ways. The best known equivalent of it is the way it has been stated by the Scottish mathematician John Playfair. The way he stated it is, in a plane, given a straight line and a point not on that straight line, one can draw at most one parallel to the straight line and through that point. One can find in the literature that the Euclidean formulation and Playfair's formulation are not exactly equivalent, but that would lead us too far. For now, we will consider them equivalent. Remark that the words at most one is very important in Playfair's formulation. We will use the formulation of Playfair as the postulate in this course. In that case, the postulate as formulated by Euclid becomes a proposition because it can be proven using Playfair's version. The parallel postulate has a whole history behind it. While the four other ones are fairly obvious, after a while people started to notice that the parallel postulate isn't. First of all, this postulate is much more complex than the other four. The other four are mostly statements about basic elements and the assumption that they can be constructed. Many mathematicians thought even that it wasn't a postulate at all, that it could be proven using the other propositions. All attempts to prove it, however, failed or used assumptions that in themselves were also postulates. In the 18th and 19th century, mathematicians finally came to the conclusion that having this postulate was not in fact a necessity for a valid geometry. By replacing the parallel postulate by another assumption, they arrived at geometries that were as consistent as when the parallel postulate is accepted. Those geometries are called non-Euclidean geometries. Before the discovery of this, the use of the adjective Euclidean wasn't even necessary. There was only one possible known geometry. But after these discoveries, it became necessary to name the geometry in which the parallel postulate holds, and therefore we named that geometry Euclidean geometry. This was a big deal, because before this breakthrough, Euclid's Elements presented an absolute truth. Now it became apparent that other systems could also exist, and we can arguably state that this revolutionized not only mathematics but science and philosophy as well. As this course is on Euclidean geometry alone, we will not further investigate the other ones. So here we accept the parallel postulate as our absolute truth in this course. And with the definition of parallel lines and the postulate, we will construct the rest of the Euclidean universe. First, we detail a direct corollary to the parallel postulate. When a straight line intersects another straight line, it will also intersect every straight line parallel to that other straight line. Let's look at a figure. Straight line CD intersects straight line AB, and CD will also intersect EF, a random other straight line parallel to AB. So CD intersects AB in O. EF is parallel to AB. If CD does not intersect EF, that would mean that she is parallel to EF while going through O. But we already have one straight line parallel to EF and going through O, namely AB, by construction. So that would mean that we would be able to draw two separate straight lines through O that are parallel with EF. As we know from the postulate that there is only one parallel possible going through a point and parallel to a line, we must conclude that this is conflicting. So CD must intersect EF. By the way, for straight lines that intersect two other straight lines, specific terminology exists. But you will have to wait a couple of lessons before I introduce this. Let's now look at the proposition that will tell us something about parallel lines, but for which we do not yet need the parallel postulate of Playfair. Proposition 21 states that two straight lines in the same plane that are perpendicular on a third straight line are parallel to each other. Suppose we have AB and CD that lie in the same plane and both are perpendicular on EF. A and C are the feet of the two perpendiculars. Assume that AB and CD intersect each other, say in a point O. In that case, we could drop two perpendiculars from one point on a straight line. This is not possible as we have seen in proposition 4. Ergo, AB and CD do not intersect, or in other words, they are parallel. The consequence of this proposition is that we can draw a line through a point outside of a straight line that is parallel to that straight line. We can show this as follows. We are given a point A outside of the straight line BC. We can construct a perpendicular from A on BC. It intersects BC in D. But we can also erect a perpendicular on AD in the point A. Let's call this perpendicular AE. We now have two perpendiculars on AD, namely DC and AE. So the proposition 21 learns us that DC and AE must be parallel. Remark that we did not need the parallel postulate to prove this proposition or to prove that we can draw a straight line through a point parallel to another line that does not contain the point. On the other hand, the formulation of Playfair does contain a part that we cannot prove. That is, that there can be at most one such a parallel. Combining the proposition 21 and the parallel postulate, we can make another corollary. Two straight lines, one oblique, another perpendicular, on the same third straight line will intersect. Let's look at the construction. We have a line that is perpendicular on a straight line. Specifically, CD is perpendicular on AB. And we have an oblique line, EF, on AB. The feet are respectively D and F. We need to prove that EF and CD have to intersect. Let's construct a perpendicular on AB in F, call it GF. The proposition 21 tells us that GF must be parallel to CD. Let's now assume that EF does not intersect CD. In that case, EF must be parallel to CD. But we already have GF that is parallel to CD. So this leads to a conflict with the parallel postulate. There cannot be two different lines parallel with CD going through F. That's it for this introduction to parallels. There are a couple more very general and simple propositions, but that will have to wait until next lesson. If you like this series, consider subscribing to my channel.